Neil, we have a very good model for the universe, the lambda CDM model.
Yes.
Where it predicts, or at least it can take us from the Big Bang
Yes.
all the way up to where we are today.
Yes.
It can predict the evolution of the universe with the components of matter, dark matter,
Yes.
dark energy, okay,
Right.
terms that we don't know that much about,
Right.
but it can tell us about the evolution.
Yes.
Now, to get the perturbations,
Yes.
the fluctuations that we
Yes.
see in the CMB background,
Right.
the fluctuations that grow to the structures that we see today,
Yes.
we need to have something happen very early on.
Yes.
And people have been speculating or proposing this to be called inflation,
Right.
right? And but there seems to be problems with this model here.
Yes.
You cannot say it's a single model. It seems to be able to predict everything, so it's difficult to rule it out.
Right.
And I know you have some new ideas both to deal with this problem,
That's right.
also highlighted the problems in inflation
Right.
and the possible solution to that.
Yes.
So can you take us through where we are?
Yes. So you're right. The surprising thing about the observations today is that they are consistent with an extremely simple overall description of the universe called the lambda CDM model. So from the fundamental physics point of view, this model has 5 numbers which we have to dial to fit the data, but it's only 5 numbers.
And what are those 5 numbers?
3 of them are to do with the different kinds of matter in the universe. So we have the cosmological constant, or dark energy. It's not really a surprise that it's there. It was the first form of matter proposed by Einstein in 1917.
But for other reasons that to explain, or
No, Einstein believed, quite reasonably, that the only sensible universe was one which is static. And because matter attracts, the universe will collapse if you only have matter. And so you can't have a static universe and just have matter. So he put in a cosmological constant which repels and balanced the two to get a static universe. So he introduced the cosmological constant, what we now call dark energy, on the grounds of simplicity and economy. It is the simplest kind of matter. It's completely featureless, it's constant in space, it's constant in time, it's just one number, the same number everywhere. It doesn't clump or doesn't do anything. So amazingly, we now discover that 70% of the matter in the universe is in this form, anticipated by Einstein in 1917. So that's the cosmological constant. Then we have the dark matter. So we see in the formation of galaxies and the structure of galaxies and clusters of galaxies, we see strong evidence that there's some other kind of matter which also gravitates and helps the growth of galaxies, but doesn't interact with light at all, so we can't see it directly. And one of the this is, of course, a big clue to physics beyond the physics we know, that there seems to be this other kind of matter. One of the original inspirations for my recent work is that we realized there's a simplest explanation for the dark matter, and it's not so complicated. The dark matter, the best candidate for the dark matter, I believe, is what's called a right-handed neutrino. So in the standard model, we have 3 neutrinos. These are well tested in the laboratory. They're strange particles because they couple very weakly to other particles.
Means that they're difficult to
very
measure,
hard
very
to do
difficult
experiments.
to see.
Yes, they have been called ghostly particles because they can travel right through the Earth, for example. So they're hard to detect. But we now know these neutrinos, and we're very used to them. What was discovered is that they have tiny masses. The neutrinos we see, called left-handed neutrinos, because if they're traveling in this direction along your thumb, then they're spinning with the fingers of your left hand. So the ones we see are left-handed, and they have small masses. And the simplest explanation for their masses is that there are also right-handed neutrinos in nature, but these are very, very heavy. So the explanation of the masses of the left-handed guys is they travel along, and then occasionally they what's called quantum fluctuate into a right-handed one, which is very heavy, and then they have to fluctuate back into a left-handed one. So it's called a virtual right-handed particle. This turns out to be the most economical explanation for neutrino masses, and it suggests that there are right-handed neutrinos in nature. What we realized is that there are 3 left-handed neutrinos. It would be very natural to assume there are 3 right-handed ones. What we realized recently is that it's perfectly possible for one of those 3 right-handed neutrinos to be stable, and it doesn't interact with the forces we know, electromagnetism, strong force, weak force. It's absolutely neutral. And the new thing is we figured out how to calculate how it was produced at the Big Bang. So we could predict its abundance. So the dark matter, in my view, is probably this right-handed neutrino. If it exists, and if it is stable, as it has to be the dark matter, it follows that the lightest left-handed neutrino is actually massless, exactly massless. The reason is, if you want the right-handed guy to be stable, you do not want it to decay into the left-handed guy. So you must switch off that coupling. But that means the left-handed guy cannot oscillate into the right-handed guy, and therefore it must be massless. So we have this clear prediction, and amazingly this will be checked in the next 3 or 4 or 5 years by galaxy surveys, because galaxy surveys are now so sensitive that they are able to infer the masses even of neutrinos, these tiny masses of neutrinos, by measuring how strongly galaxies themselves cluster.
But here you're saying that it is really not a measurement of this massive one.
No.
But it's a measurement of the lighter one.
Exactly. So our explanation of the dark matter predicts that the light one should be massless.
Massless. And that's
that will be tested.
Yeah.
If that test turns out to be positive, that indeed the lightest one is massless, I believe this explanation for the dark matter is easily the most plausible.
So if we're going to the inflationary picture,
yes.
It also claims to be able to solve whatever you're going to observe at some point, right? Or observing currently. Where is that tension, or why is there a problem?
Right. So inflation has been around for 40 years. I was actually very fortunate, and I attended as a graduate student the first workshop on inflation held in Cambridge, which is a famous workshop where people first spoke about this mechanism for making the fluctuations that lead to galaxies.
Is it true, like we have these, you can think about it maybe as quantum fluctuations very early on.
Yes.
You have an enormous stretching, right? And you basically, manifest these fluctuations into the real matter that we see today.
Exactly. So it's a very, very beautiful idea. That because we know from all of the physics that we do of the Standard Model that the fields which describe all the particles and forces do fluctuate in the vacuum. They cannot stay still because of the Heisenberg uncertainty principle, so they're always oscillating. And these oscillations in the vacuum get blown up by expansion, by inflation, into very large-scale fluctuations in the density of the universe. And this is what we see.
And just to make sure this is not part of the lambda CDM model, say it's something we have to stick to the model in very early times, right?
Right.
So you have a little freedom in how it all started before you get into the standard evolution. Is that right?
So lambda CDM is just a parameterization of these fluctuations. It's an amazingly simple parameterization because it uses only 2 numbers. One is the overall amplitude, by how much the density varies across the universe as the universe came out of the Big Bang. That number is about 1 part in 100,000. So it's a very small variation. The second number tells you that the variations are slightly stronger on long wavelengths, only by a very small amount. So as you go to bigger and bigger scales, the fluctuations get ever so slightly larger. So just 2 numbers. And then you say these 2 numbers characterize a random field, like ripples on the surface of the sea or something. It's a really random pattern of ripples. And those ripples turned into galaxies and clusters of galaxies, CMB fluctuations. All of this is explained with just 2 numbers. So it's very remarkable. Now, That's a lambda CDM model, which does not explain those numbers. It just fits those numbers to the data.
In time, yeah.
And remarkably, to fit all the data we see, many, many different measurements, these same two numbers fit everything consistently. Of course, there's some tensions. At the moment, people are worried about the Hubble constant, but none of these is yet compelling. None of the difficulties in fitting the data with this model is yet at a level where you really need to, where they disprove the model. We're nowhere near that. This model is doing amazingly well. Now, inflation, one of the reasons it became so attractive is it provided this mechanism which could explain these two numbers. The reason why that for me, wasn't convincing is, as you said, there are a huge number of inflation models. You don't explain these two numbers either. You just adjust the models to fit the numbers. And you've got 10,000 models to choose from. So what have you explained? Okay, you've just pushed the problem somewhere else.
You can also say, how can you rule out the model? You're putting forward something, can you rule it out? No,
exactly.
That's the problem.
Exactly. So in my career, I've always been interested in theories you can rule out. Okay, because I want to know. I do not want to work on something that's why I'm a physicist rather than a mathematician. I want to work on something which ultimately is tested against nature. Nature is the final judge, So
what is different in your model here in this?
So we started about 5 years ago trying to ask foundational questions. Why is the universe so big and smooth and flat? Which inflation answered by expanding, blowing things up and flattening it out.
Smoothing things out,
yes.
You can say, yeah.
And we realized there's a different explanation. And that different explanation uses a concept of gravitational entropy, which is still mysterious, but it was one of the key insights Stephen Hawking had about black holes. Now, to draw an analogy, when we look at this room and the air in this room, it's very smooth. It's what we say homogeneous. It's the same at every point, the density of air, almost the same, and it's isotropic. Why is that? The reason is very simple. It's thermodynamics. That if you throw a bunch of air molecules in a room with a certain energy and you leave them to settle down, this is the most probable state.
Exactly. It's most likely that it's like this.
Likely.
Then all of them is being up in the right corner.
Yeah. Exactly. The most likely state is homogeneous and isotropic. And we say that state maximizes the entropy. Now, what Hawking gave us is a way of calculating the entropy. He didn't do this, but we have applied it to cosmology. So we can calculate the gravitational entropy of a universe with lambda, with the cosmological constant, matter, radiation, spatial curvature. So space could be bent. And we recently calculated this, and then we asked which universes have the greatest entropy. And it turned out that the most probable universe is spatially flat, and it is homogeneous and isotropic. So that is a consequence of thermodynamics. You do not need a mechanism to explain it. Okay, so my current belief, and based on this calculation, is that the universe we see around us is in fact the most probable universe. And all you need to explain that is Einstein's theory of gravity, the standard model of particle physics with these right-handed neutrinos for the dark matter, and Stephen Hawking's method of calculating the gravitational entropy.
But what about the fluctuations?
Good. So we started off by explaining the large-scale geometry, the simple character of the universe. And then the obvious question is, what about the fluctuations? It's not perfectly homogeneous. Where did they come from? Again, we went back to first principles. It's very plausible that what we're seeing in these fluctuations are the quantum fluctuations from the vacuum. That's very plausible. They have the same statistical properties as the fluctuations in a quantum field in its vacuum. So they seem to fit. The reason people needed inflation is they used certain kinds of quantum fields. Historically, people focused on fields, technically you say, with only two derivatives in the Lagrangian. What we realized, and this is about 5 years ago, is that there are other kinds of quantum fields which are potentially possible, could exist in nature, and they have four derivatives in the, okay? So they're a little bit weird. They're an extent beyond Newton. You know, Newton only had two derivatives. Maxwell only had two derivatives. Einstein only two derivatives. These have four. But they have many, many beautiful, very beautiful features. So this subject had been bubbling around in the literature for a while. People like Dirac and Heisenberg and Bogolyubov had studied them. But what we realized is that if those fields exist in nature, they have the right properties to explain what we see in the sky. Now, what role do these fields play in the standard model? That was the question. And then we discovered something amazing. So it's well known that in quantum field theory, these vacuum fluctuations, if you add them all up, they contribute infinite energy, right? It's a huge paradox that the wavelengths of arbitrarily short wavelength oscillate in a vacuum. They all carry energy.
Yeah.
Add it up, you get infinity. Yeah. Okay, something is wrong because gravity sees that infinity. So people have found various ways to disguise this in quantum field theory, but it leaves you very queasy. It means we don't really understand something about how gravity couples to these quantum fluctuations. There are similar problems called anomalies. The standard model, if you write it down classically, has certain very beautiful symmetries. One of them is called local scale symmetry. You know, with the Maxwell equation, an X-ray is the same as a photon, it's the same as a radio wave. They're all identical, they're just scaled up and down.
Wavelengths.
Different wavelengths.
Exactly, yeah.
Okay. So, and there's even more symmetry because Maxwell's theory, if I change the scale in space-time locally, it's still unchanged. Okay, so I can distort space-time locally with the scaling, and there's no effect on Maxwell's equation at all. So it's amazing symmetry. Dirac's theory, if you ignore masses, has the same property, scale, locally scale invariant. Very beautiful. So it turns out these anomalies spoil that. The quantum vibrations in the vacuum, because they're divergent, spoil these symmetries of the theory. So it's a deep problem. What we realized is that by adding these four derivative fields, we cancel all these problems at once.
I see.
The vacuum, and only at the first level of approximation, I emphasize, because this is only a sort of very preliminary indication. But it's still amazing. There was a sort of numerological coincidence that if you add the right number of these fields, you cancel three problems at once. And no one ever did that before. You cancel the vacuum energy, and you cancel these local scale anomalies. So then, using this, we said, okay, let's use these fields to cancel the violation of local scale symmetry. Now let's go to the Big Bang. The Big Bang is the place you really want to have local scale symmetry. Why? Because the whole universe is going to zero size. Now, good luck with doing physics when the universe is zero size. It's a point. Yeah. You can't do anything. There are no differential equations, nothing. So some people, and most people, would just say, give up. You know, you're not going to describe the singularity. Not so fast. Because if all the matter in the universe is locally scale invariant, it doesn't know about the size of the universe. It doesn't matter. No. So you trace it back to the Big Bang, and as far as the matter is concerned, everything's fine. So this is what we discovered. We discovered that we can actually describe the Big Bang. We can, what the technical method is called analytic continuation. Basically means that the functions involved are smooth. You can follow them right through, and you can describe the Big Bang itself.
So to boil it down in your model,
yes,
you have to add two components
Yes.
to what we already know. That field that we're talking about
Yes.
in the right-handed side, neutrinos.
Yes. So now when you say add, I won't quite go along with that, because the right-handed neutrinos, we're almost certain they need it anyway.
That could be, yeah.
Because we
That is
we
right.
know
We see the
the left-handed guys have
measure
small
them.
masses.
That is right.
So we haven't really added anything. The people who added it were in the 1970s. They added it, and I think they did a beautiful job at explaining. So we're just using that.
You're right.
So I define the standard model to include them.
Yeah.
Now, these other fields, they have a very bizarre property, which was realized in the 80s, but not appreciated by the physics community. Their property is that they don't have any particles. They only have a vacuum. It's the only state in the theory. So the vacuum of these new fields we're adding is unique. All it is doing is actually fixing the vacuum of the standard model so that it is compatible with the local scale symmetry and zero energy at the first level of approximation. So I would say it's a compulsory addition to the standard model. Without these fields, the standard model doesn't make sense, coupled to gravity. So what we see is that by introducing these things, they then perturb the universe coming out of the bang. And then the kind of miracle that happened in our paper we came out with in February is that we calculate the strength of the fluctuations and the small tilt from first principles and it agrees with what we see.
And the model that you have is testable. You can
Yes,
rule it out.
absolutely.
And as we talked about,
absolutely.
Right now, the surveys are out there measuring
Yes.
the masses of the neutrinos, which is the key point
Yes.
in
But
the...
not just the neutrinos, the fluctuations,
The fluctuations,
too.
yeah.
So we have only done the first calculation of these fluctuations. There are theoretical uncertainties. We included some things we didn't include. Those have to be refined. On the observational side, we're going to measure the power spectrum of fluctuations more and more precisely. If the theory and the observation continue to agree, this will become completely compelling.